In shared memory IPC, processes read and write into a shared memory region. The operating system is involved in establishing the shared memory channel between the processes. What this means is that the operating system will map certain physical pages of memory into the virtual address spaces of both processes. The virtual addresses in P1 and the virtual addresses in P2 will map to the same physical addresses. At the same time, the virtual address regions that correspond to that shared memory buffer in the two processes, they don't need to have the same virtual addresses. Also, the physical memory that's backing the shared memory buffer does not have to be a contiguous portion of physical memory. All of this leverages the memory management support that's available in operating systems and on modern hardware. The big benefit of this approach is that once the physical memory is mapped into both address spaces, the operating system is out of the way. The system calls are used only in the setup phase. Now, data copies are potentially reduced, but not necessarily completely avoided. Note that for data to be visible to both processes, it actually must explicitly be allocated from the virtual addresses that belong to this shared memory region. So if that's not the case, then data within the same address space has to be copied in and out of the shared memory region. In some cases, however, the number of required copies can be reduced. For instance, if P2 needs to compute the sum of two arguments that were passed to it from P1 via the shared memory region, then P2 can only read these arguments. It doesn't actually need to copy them into other portions of its address space, compute the sum, and then pass it back. However, there are some drawbacks. Since the shared memory area can be concurrently accessed by both processes, this means that the processes must explicitly synchronize their shared memory operations, just as what you would have with threads operating within a single address space. Also, it is the developer's responsibility to determine any communication protocol-related issues, such as how are messages going to be formatted, how will they be delimited, what are their headers going to look like, and also how the shared memory buffer will be allocated, when which process will be able to use a portion of this buffer for its needs. So this adds some complexity, obviously. Unix-based systems, including Linux, support two popular shared memory APIs. One of these was originally developed as part of System 5, and the other one is the official POSIX shared memory API. In addition, shared memory-based communication can be established between processes using a file-based interface, so via memory-mapped files in both address spaces. This API is essentially analogous to the POSIX shared memory API. Also, the Android operating system uses a form of shared memory IPC that's called ASHMEM. There are a number of differences in the details of how ASHMEM behaves compared to the System 5 or the POSIX APIs, but I'm just providing it here as a reference only. For the remainder of this lesson, we will focus on briefly describing the Unix-based shared memory API.